Ladies and gentlemen, please welcome Bram Vanderborght to the stage.
Good afternoon. I will talk, of course, about robots, and specifically about robots need somebody. And in fact, that has two meanings. First of all, somebody, so a smart body, because we will see that by this we can outsource intelligence from the mind to the body and simplify the task for the robot. And the other meaning is we need somebody, the robots need somebody, another person, because we will see that humans and robots have different strengths. And I think we need to combine those strengths and go for human-robot collaboration instead of robots replacing humans. But first, go back in time to Descartes. So he thought that there is the mind, which is a thinking thing, which is completely disconnected from the body, which is the non-thinking thing, to be the slave of that mind. And that is also used as the computer metaphor of thinking, where you have the input, and then the mind, and then the output. And that led and is still leading to very impressive results. Think about IBM Watson, AlphaGo, and many other impressive applications which will come. This metaphor is also often used as a computer metaphor for thinking of robots. Of course, then you need a body, and so in the body, there are the sensors to sense the world, and that information is sent to the mind, where it's then processed, and then the output is to actuators, the motors of the robot, in order to control its environment. And this is very successful, for example, in the industrial robots, for example, building our cars. But there's also some drawbacks. And here you see, for example, a coconut being crushed by an industrial robot. And why I show here a coconut? Because the force to break such a coconut is about the same force to break the human skull. So those robots are extremely dangerous. And that's why they have to be kept safely in cages, and they replace human work. And it even gets worse for robots when we place them in unknown environments, dynamically changing environments. And trivial things for the human, like walking or running or opening doors or handling tools, become extremely difficult for those robots. While on the other hand, we see the inherent capabilities of the human body. Because of the smart design of our body, we're able to absorb huge impact shocks. We are able to move very energy efficient and also very safely interact with our environment. So by the smart design of the body, we can do much more. And this is also shown by this video of a decerebrated cat. So that basically means that the brain is disconnected from the body of the cat. And you see that the cat is able to walk and even exhibit multiple gait patterns. So where is the intelligence? The intelligence is not only in the brain of that animal, but also in a smart design of the body of the cat. And this is thanks to millions of years of evolution that the cat could adapt its mind and its body to interact with the environment. And this evolution didn't happen yet with the robot bodies we want to develop. So you can see, for example, Asimo, a very impressive robot running, but in order to do so, he needs to process a huge amount of data in order to keep balance and so on. So a very versatile robot, but you need a lot of processing power, much faster control loops than, for example, the nerves of the human body. And then you have, on the other hand, passive walkers. And they don't have any control at all. Even to walk down a slope, they don't need at all motors, because they saw that the human body has a smart design consisting of a set of pendulum motions. For example, swinging the leg, there is almost no muscle activity in our body. Also, foot clearance, bending the knee while walking, that happens by exploiting the natural dynamics of your system. Of course, when you need to walk over level terrain, you need a bit to overcome friction. And then the control is also very simple. When the foot touches the ground, swing the other leg front, swing the other leg, and so on. So very simple control, very energy efficient robots. And when Asimo is running, you see that he has that funny run. And the reason is, at touchdown, he will hurt his motor. So what he has to do, he has to sense that he's touching down, and he has to retract the leg in order to dissipate all that energy. But that means during the next jump, he has to use his batteries in order to inject energy back in that system. While how humans run, we don't run like that. We run like a bouncing ball that stores energy and releases it without dissipating so much energy. And that's very visible, for example, when you see Oscar Pistorius running. He didn't have legs, so he has two very energy-efficient springs, blades. That's why he's called the blade runner. And they are tuned to run at a very high frequency, capable of running the 400 meters. He didn't have the muscles to accelerate as much as the others with the sound leg, but once at speed, he could more easily keep up that speed. That's also the reason why he runs the 400 meters and not the 100 meters. But his design of this prosthesis is optimized for that running speed. So when he goes to regular walking, he has to replace his prosthesis. And then he wears prosthesis which immobilize so he cannot move his ankle. That has a drawback that you can compare it a bit with walking with closed keyboards. So it goes slower, one consumes more energy, one has an asymmetric gait, and so on. So that's why we started to develop a new generation of prosthetic bionic feet, in which we try to make a smart design by including locking mechanisms and springs so it adapts naturally, for example, the different terrains. By using springs, we can store energy during one phase of the motion and release it during another phase of the motion. So by a very small design, we can outsource intelligence from the brain to the device. If you want to know more about this prosthetic feet, you have to return during the weekend, because this startup company of the VEB will exhibit in the MAS. This is a prosthesis for the an amputation below the knee. We have also prosthesis for amputations above the knee. And you see that person has difficulties to climb stairs. While when you introduce also motors in the knee, he can more easily control the knee. Does it mean you don't need any artificial intelligence or intelligence in the brain at all? That's also not the case, because on the right slide you see that we participated in Cybathlon. And Cybathlon is a kind of Olympic Games for people with a disability, but assisted by technology. And before any task, he had to touch a touchscreen, like lift my leg, or climb stairs, or sit in a chair and go out again. So that's not very practical. So we're developing deep learning methods that, based on the sensor information from the prosthesis, will predict in which kind of gait pattern the user is. So again, a combination of intelligence from the mind and a smart design of the body. A similar thing happens with grasping. Very difficult for robots. Our hands are also very complex. We have 20 muscles in the hand to grasp different objects. But 80% of our daily grasps are just closing our hands. And because we have a smart design of our hand, due to the softness in our hand, we can automatically adapt to different forms. So that we achieved here with those soft pneumatic grippers, due to the softness, there is no control, there is no sensing in it, it can grasp different objects. But like the human body, those soft materials, like the soft materials in our hand, can be damaged. For example, there can be sharp objects that can damage it. And our human body has some impressive capabilities to self-heal. We can heal wounds, and we can heal broken bones, And that we try to solve with introducing self-healing materials. So here you see a kind of polymer. It's a network polymer that we cut in two. And normally you would need glue or tape to connect them again. But here we just place the two parts together and the material will heal. The reason is inside the material are reversible bonds. So if we cut the material, we cut them on those reversible bonds. And when we place the material back together, those bonds will reconnect and the material will heal. On the right, you see a video of under the microscope, also 400 times faster, where you see that this material is healed. So also here, do we need intelligence? Yes, we need a lot of intelligence. Probably the reason why we started to have such a big brain compared to other animals is that we started to use our hands. So it uses a lot of computational intelligence from us. But by outsourcing with a smart design intelligence to the hand, we can simplify the intelligence from the mind. And then I think we need human-robot interaction, because computers can process a huge amount of data that we as humans cannot do. We cannot even multiply 21 with 431 in a reasonable time. On the other hand, we don't need thousands of iterations to learn something new. We are very creative. We are very dexterous. We are very creative. While robots can be much more precise, or doesn't get tired, or can work in very dangerous situations. So I think we need to combine those complementary strengths between the human and the robot to solve our societal challenges. And one thing is that humans and robots need to work together in companies. And on the left, you see an operation that was done at Audi Brussels to do a glue operation, but that was not done very precisely for the quality needed for the car. So that had to be replaced by a robot, but the human was necessary in order to place that component in the car. So humans and robots, Audi wanted that humans and robots started to work together. But working together also means interacting, communicating with each other. And how we communicate? Via speech, but also with emotions and gestures. And you see during the IME Klaxon project with also RoboVision, and Jonathan Berthet will talk tomorrow on this stage and give more information, you see that the worker is able to show gestures and the robot is able to understand. So at the moment, there is not yet a physical collaboration between the human and the robot that we develop further in the Flanders Make project Eve, where the robot detects the ergonomics of the worker, if he is bent too much to the front or his head is bent too much. That's not good for his health. So what we do, the robot will adapt his collaborative task so that humans and robots can better collaborate. Another possibility is not having the robot next to you, but just to wear the robot. And that are called the so-called exoskeletons. So that are wearable robots. Of course, safety is here very important. For example, on the left, for rehabilitation, for people after a stroke or a spinal cord injury that lose the ability to walk and sometimes be retrained, and we develop dedicated robots for that. Or persons, for example, with a muscle weakness, when they have to go out of their chair, it's like an electric bike. You still have to pedal yourself, but assisted by this technology. So that are examples of human-robot interactions. We also have social interaction, and we use them, for example, with children with autism. They have difficulties, for example, in joint attention. So when I look to the screen or when I point to the screen, you can follow my gaze, but those children have often difficulties with it. So for the therapist, it's very difficult to do that, because at that moment, he or she cannot concentrate on the child. So the robot, you see that it detects the eye gaze of the child, he detects his gestures, and the robot will respond automatically. And the task of the therapist is there to focus more on the child itself and assist him or her. So as a conclusion, I think robots need somebody. So they need embodied intelligence, as we call it. They need a smart design to outsource intelligence to the body. Moreover, robots need somebody. They need humans. because humans and machines have different strengths, and we need to evolve towards human-robot interaction. Thank you very much.